Now we look at an example and see how all this is connected with probabilities. If the probability that a person is left-handed is 0.1 and 9 people are chosen from a large group, find the probability that there are exactly 4 left-handed people in the 9 people chosen. Okay, so what are we going to do if we want to solve this? We want 4 left-handed people. Well, let's suppose that the first 4 people are left-handed and the next 5 are not. We're assuming that the probability that someone is left-handed, is an independent of the probability that anybody else is left-handed. So if we have the line as I've written there, the probability of that line is going to be 0.1 times 0.1 times 0.1 times 0.1 times 0.9 times 0.9 times 0.9 times 0.9 times 0.9. That is 0.1 to the 4 times 0.9 to the 5. But we might not have chosen our 4 left-handed people like that. We might have chosen the first 3 to be left-handed, the next one not, and the 5th person left-handed, and the rest not left-handed. Our probability in this case would have been 0.1 times 0.1 times 0.1. Next person was not left-handed, 0.9. The next person was left-handed, 0.1, 0.9, 0.9, 0.9, and 0.9. And once again, we have 0.1 to the power 4 and 0.9 to the power 5. So whatever order we choose our 4 left-handed people, the probability of that arrangement is still 0.1 to the 4 times 0.9 to the 5. Well, from what we've just been doing in the previous video, we know that there are 9C4 ways of choosing the 4 left-handed people from 9. Well, 9C4 is 9 times 8 times 7 times 6. That's 4 numbers on the top line, divided by 4 factorial. 3 times 2 cancels with the 6. 4 into 8 goes 2. 7 times 9 is 63, times 2 is 126. So if we put those ideas together, every line has a probability of 0.1 to the 4 times 0.9 to the 5. We've got 126 possible lines. The probability, therefore, that L, the number of left-handed people, is 4, must be 126 times 0.1 to the 4 times 0.9 to the 5. If we press the buttons on our calculator, this is 0.00744 to 3 significant figures. In this instance, we say that the number of left-handed people, L, form a binomial distribution. The numbers of left-handed people, L, form a binomial distribution and we write L twiddle B 9.1. 9 is the number of people, and 0.1 is the probability of a left-handed person, the probability of success. Well, let's generalize this. Let's see what happens if we have a look at the binomial distribution in general terms. We write BNP, and when we write BNP, we mean that that is the number of trials, like the number of people just now was 9, and P is the probability of success in any one trial. In other words, the probability that one person is left-handed was 0.1. The conditions for a binomial distribution are: a single trial has 2 possible outcomes. We've just had a situation where a person could be left-handed or not left-handed. This trial is repeated a fixed number n of times. We selected 9 people, so in the previous example, n was 9. The n trials are independent of each other. The fact that one person is left-handed doesn't affect the probability of another person being left-handed. The probability of success, P, remains the same for each trial. We assumed that the probability of left-handed was 0.1 for every person in the group. Let's take these ideas now of our left-handed people and see what we had. We had L twiddle B 9.1. The probability that L is 0, well, the probability that one person is not left-handed is 0.9. The probability that none of them are left-handed is 0.9 to the 9. Probability that L is 1. Well, we want one left-handed person. We want 8 people who are not left-handed, and that can be done in 9C1 ways. We can choose one person left-handed from 9 in 9C1 ways. Probability that L equals 2. Well, here we want 2 left-handed people. That means that we have 7 that are not left-handed. 0.1 squared times 0.9 to the 7. How many different ways can we choose the 2 left-handed people? Answer 9C2, and so on. What I want to do now is to take those ideas and generalize them. If we take X is a binomial part of a binomial distribution BNP, then in the same way, the probability that X is equal to 0. Well, the probability that we have success, like one left-handed person, is P. The probability that we have failure is 1 minus P. So the probability that X is 0 will be 1 minus P to the n. The probability that X is 1, well, I want 1 success, that's P. I want n minus 1 failures, that's 1 minus P to the n minus 1. And how many ways can I choose 1 success? NC1. The probability that X is 2. Here we want 2 successes, like 2 left-handed people. 2 failures, so n minus 2 failures. And how many ways can we choose the 2 people from n in C2? If we carry on in the same way, the probability that X equals R, well, here we want R successes, that's P to the R. We want n minus R failures, that is 1 minus P to the n minus R. And we have NCR ways in which we can choose are R successes from N. It's the last line which gives us the basic formula for dealing with binomial distribution. If X is binomial NP, then the probability that X equals R is NCR, P to the R, 1 minus P to the N minus R. That is the formula which you will find in your formula book, and it's also obviously in your textbook. Let's see how this works in practice. If we take an example, as written down here, in a game, the probability of winning is 0.73 and losing 0.27. Find the probability of winning in more than 7 games and in 10 altogether. Well, we can see that this follows the conditions for a Poisson distribution. It has 2 possible outcomes. You either win or you lose. We're talking about 10 games, so we have a fixed number of games or a fixed number of trials. If we assume that this is a game of chance, then the trials will be independent of each other, and we would then expect the probability of winning to remain the same, 0.73 in each trial. So let's solve this problem now. The number of successes, the number of wins, X, is binomial. Number is 10, and probability of success is 0.73. In any solution to a problem, you should always start by saying exactly what you're doing. This bit, B, N, 0.73, is your method, your explanation, which justifies everything that you're going to write down afterwards. It must always be there. We're looking for the probability that X is bigger than 7. This is the probability that X equals 8 or 9 or 10, which will be the probability that X is 8 plus the probability that X is 9 plus the probability that X is 10. This is where we need the formula at the top. The probability that X is R is NCR, P to the R, 1 minus P to the N minus R. So the probability that X equals 8, needs a bracket, is 10C8 times 0.73 to the 8 times 0.27 squared. The probability that X is 9 is 10C9 times 0.73 to the 9. Let's make that just a bit tidier. 0.73 to the 9 times 0.27 to the 1 plus 0.73 to the power 10. Pressing the buttons on your calculator, you get 0.3470923 ... And it's always sensible to give 3 sig figs in your answer, unless told otherwise. 3, 4, 7, 3 significant figures. So that is the answer. The probability that there is more than 10, 7 more than 7 wins is 0.347. You can find more about the binomial theorem if you look in the textbook S2 on pages 5 to 8.